Hey guys, what's happening? Oh, that's not right. Oh, no, that is right. I'm sorry. So we didn't code yesterday. Yesterday I ended up driving. I work for the UPS, and they asked me to cover drive in not Covington, Gonzales. So I was it's an hour drive roughly, and yeah, worked 12 and a half hours. So I'd only gotten like a little bit of sleep anyway the night before, for whatever reason. I got like 5 hours of sleep. Woke up at like 2 in the morning, couldn't go back to sleep. Had to be at work at like 5, so I slept from like 9:30 to 2 at night. So I was running off of like, I don't know, what, 5 hours of sleep or something. And dude, I was so freaking exhausted by the end of my shift. I didn't get home till like 7 o'clock. Anyway, so didn't code yesterday, but the day before that was the last session, and that was when we did continue working on code to reconnect, finish implementing the token creation. Alright, so we finished the token creation and verification code in server and hash token pi. We began refactoring associated code in network pi, such as get client and name ID, to conform to these changes. Excuse me, and we stopped at line 58 in network pi, so let's go over there. These changes began refactoring. Okay, so this will say continued. Alright, so is it network, right? So this is client, server, or network rather. Alright, so this is where we had stopped. So I could receive, how much bytes to receive. Oh, forgot to set my timer here. Okay, so this is where this is the specific line that we stopped at. So we have to determine how many bytes do we receive. So this corresponds to the code here in server, where we generate the client. Well, no, am I reading this right? Right. Okay. Generate. We can delete this file, the hash token GPT one. All right, so we have final form is a string, but how many like bytes is it gonna be? Well, honestly, we could probably just ask ChatGPT this, and it will be able to tell me exactly how many bytes this is. Well, does it? Well, is it going to depend on how big the payload is? That that is like, it might not be a set amount of bytes. You know what I mean? It might not be that way. We might just have to do like the whole send. Let's check the audio here. That is like, it might not be a set amount of bytes. You know what I mean? It might not be that way. We might just have to do like the whole send. Oops. Dumbass. So the audio is working. Welcome to the internet. Okay. So we have to copy this. Let me think about this for a second. Because this might be solved by, instead of receiving a certain amount of bytes, just receiving, like, is there a way to, well, we have to send a header first, right? Yeah. It's just like the normal, it's like the normal way that we send and receive stuff. We normally create a header that tells us how much we're receiving, like how many bytes to receive. So the first one is the header, and that is a fixed length. So it's a fixed amount of bytes, so we know exactly how much to receive. And then we receive the number of bytes that's contained inside of the header. Let's see, so we have header amount, okay, and header string, blah, blah, blah. Header amount equals int of header amount minus 33. Alright, so message header gets the size of the object that we're sending. We then turn that into a string. Then we check the length of the object size string. So if it's less than 7, we append 7 minus length of object size string. And then we pad it with the amount, pads with amount of missing len. And then byte object size string equals byte object size string. And then we return the final form, type is bytes. Yeah, and then we just send that directly. It's already encoded, right? Yeah, so then we just do send all. We take the first 7 bytes to be the header string, and then from 7 onward is the actual data. So we send it all as once, all as one send, but we do create the header first. So like, shouldn't we just do that? Shouldn't we just do this where we use the message header? So we go, how exactly would we do this? So the order of events here is we create the client token in the server-side threaded client. Then we encode it, and then we send it. But this needs to be modified. Well, Shouldn't we use send all? Okay. Yeah, I think we should use send all, but anyway, that's like, I think it will work either or. So generate client token, then we encode it, and then we send it. But couldn't we just replace this? Couldn't we just use the message header and then and this name should be changed to create message. Yeah, so we'll just call message header, and what that's gonna do is it's gonna create the header, and then we can just well, why do we do it like this? Why do we do send all 0 through 7 and then send all 7 onward? I don't think it matters, right? Because it just goes into like basically a buffer list, and all the data is like it's just a complete string, an endless string. I don't think it's actually separated per send, like per packet, whatever you want to call that. That's not actually a packet, but per send, I don't think it actually segregates that on the receiving end. I think it's basically just like you might have like a group, like families lining up at a train station line, but just because they come in like a group of 5 or 3 or 2, the line doesn't care or take into account that. It just puts them all in a line, you know? So I think we could probably just do socket send, and then honestly, like, this function is not even necessary unless it's necessary to do this division. So let's figure that out first. If we use option 2 versus option 1, will the receive end still handle the data in the same way? In TCP, socket send and send all do not guarantee the data will be received on the other end in the same chunks it was sent to. So yes, the receive side can still handle both option 1 and option 2 in the same way, as long as your receiving code correctly reassembles the expected message format. TCP is a stream protocol. Whether you use that or that, the receiver may get both parts together, or just the header first, or even just part of the header. The code must read exactly 7 bytes first, then read the remaining expected data as per your protocol. Gotcha. So the string, what is this called? The byte stream, the receive byte stream treats the data, the incoming data, like a train station line, where in families may come in groups of 3 to 5, but all end up being lined up one by one in order of reception. Yes, that's a perfect analogy. Here's how it maps. TCP as a train track, not train cars. Think of TCP as a single train track, a byte stream. The sender sends families chunks of data like headers and payloads using one or more send or send-all calls. But when those bytes hit the receiver, they arrive as a continuous line of people on the platform, not necessarily grouped as they were sent. You just see a stream of people arriving in order, but not necessarily in full groups. The order is preserved, the grouping is not. The receiver might get 3 bytes of a header in first receive, or 7 header bytes. Okay, so wait a second. How did we preserve? How did we preserve the order, though? Remember, like, we had a because whenever we send and receive, we preserve the order normally, not on the initial send. See, so we have the apply counter, and all that. And why don't we use that at the beginning? I mean, I guess it's just because we don't need it. Because I guess technically sending it in 2 different things, how do we know it will send in the proper order? Okay, so the most concise way to send would be to include the header and the payload in one send all. Diff between send and send all. Also, how do we ensure, how do we know in the header plus payload case using send all that it will be received in proper byte order? If we used option 1 instead, using 2 sends, could that cause second send being received first? Okay, is send all header plus payload the most concise? Yes. Using socket send all header plus payload sends all the data in one syscall. Minimizes context switching. Avoids TCP segmentation between header payload if they're small. Easier to reason about from a logical standpoint. The difference between send and send all. Send may send only part of the data. You must check how many bytes were sent and resend the rest manually. Keep sending until all data is sent or an error occurs. No need to loop. You send if you want fine-grained control. If you want simple, full buffer transmission. Will send all header plus payload guarantee correct byte order on the receiving end. So we just need to make sure, basically, we're always using, always use send all. According to GPT, .send will sometimes only send a certain portion of data, therefore use send all to ensure all data always sent. So send sometimes only sends portion of data, therefore send all is safer, more secure. Oh, it's the difference between send and send all. May send if you send if you want to find, choose send if you want to save it. Will send all header payload guarantee correct byte order on the receiving end? Yes, TCP guarantees the order is preserved. No interleaving, even if two sends are done back to back. But data received on the other end will be in the exact same byte order it was sent, just possibly split up. Well, we know that's not true, though, right? Well, like, yeah, because remember, we dealt with that for a long time. We had an intermittent data transmission issue wherein later, like, data that we would send a big, huge packet first, and then we would send a small packet second in a separate send, and the second send would be getting received first. So I don't understand how that could be true. Maybe it's hallucinating, or maybe it just really is meaning to say it's preserved on the sending side. But the receiving side, that's different, right? It's obviously different. Even if the OS network splits the data into multiple packets, the receiving stream will always resemble them in order. If we use two separate send calls, could the second one be received first? No, not under TCP. TCP guarantees byte order, even if you send multiple send calls. Those people will never get the payload before header unless your own code has a bug on the receiving end. Is the cleanest mode TCP guarantees order delivery? Let me know if you want. So send something. Concerning receive order, though, I had an issue on receiving end wherein I would send from server side to client side a very large send object and then a very small send object, but the second would end up getting received first on server side, receiving side. How could that happen if TCP ensures byte order? Send is unsafe unless you manually handle. What was the first question? So send some nodes only send portion data. Yeah, send is unsafe unless you manually handle partial sends. Send may only transmit part of the data. It returns the number of bytes actually sent, and you are responsible for calling send again to send the rest. Send equals sock send data. If send is less than that's, bro. Send out of this loop internally, so it's safer, simpler, and more robust, especially for multi-threaded or non-blocking apps. Now about your receive issue. You send a large object small into receive. That shouldn't happen in a normal TCP flow because TCP guarantees the receiver calls you too soon. TCP is a stream, not a message call. So if your receive looks like you could pick up only part of the large message only at the beginning, depending on timing, buffering, and OS behavior. If the large message is delayed or still being transmitted, your receive may just grab whatever is already in the buffer, even if it's the next small message. Without a protocol, e.g. a header that specifies size type, the receiver can distinguish. Is that one message, two messages, a message with... You sent the second message before the first finished sending. TCP sends data in the order your app handed it to the OS, but if you do send large data, small data, and the first send only partially sends or gets blocked on large data, the small one may be enqueued and fully sent while the first is still being flushed. So your client may receive the small one first, but that's only because the first wasn't fully received yet, not because TCP reordered anything. Always use send all, ensure full send, use a length prefix protocol. Okay, alright. So I was about to say you're calling me a liar. I was like, bro, I went through this. Someone being queued while the fully... so essentially, the TCP send system is multi-threaded, tasked to handle .send .sends simultaneously. Like that's basically you're getting how the OS and TCP stack actually manage the send buffer. Send is not multi-threaded per se, but it can appear that way due to buffering and async I/O underneath. Socket send puts data into the OS kernel send buffer. When you call socket send, you're not sending over the wire immediately. You're handing the data to the OS kernel, which queues it in a TCP send buffer, breaks it into TCP segments. Queues it in a TCP send buffer, breaks it into TCP segments, transmits it in order. So even if you do socket send big data, socket send small data, the OS may queue both, but small data might get fully buffered and transmitted first, especially if big data is very large. The kernel starts sending big data but hasn't finished. Small data fits in one segment and gets sent immediately. Yeah, so basically it's like asynchronous. It's handling one while it's also handling the other. It's not like because you called this send first and this send second, that don't matter. That doesn't actually matter. Internally, the OS kernel does multitask. TCP transmission runs in background processes inside the kernel. TCP transmission runs in the background processes inside the kernel. The actual segmentation and sending is asynchronous to your Python process. So if your app calls send again before the first chunk is fully sent, it just gets added to the queue. That's why it feels multi-threaded, but it's more accurately event-driven plus buffered I/O. Damn, so I could have just used a send lock to fix that issue I had. Damn, that's crazy. Instead of making instead of using the apply counter and stuff. Well, no, because we have multi-threaded sends, right? So I think, yeah, we probably actually needed that. Anyway, I'm not like... TCP send is buffered and asynchronous inside the OS, not true multi-threading. Ordering always preserved by TCP, but receive may return partial data. Maybe coalesce delayed or split across packets. Multiple threads using... So, how does the small send get ordered mixed in with the large send? How does it know that's a complete send? This is exactly the heart of the issue. The key misunderstanding is in assuming TCP deals in messages or complete send. TCP does not preserve send boundaries. It preserves byte order, but not send call boundaries or messages. So when you do sock send large data, say 10,000 bytes, the OS puts both into the TCP send buffer as one continuous stream of bytes. Socket receives, it doesn't actually receive small data first. What happens is more subtle. If received doesn't know the size of each message, it reads whatever available first. You send, okay, 10 kilobytes, 10 bytes. On the receiving end, reads up to 124 bytes. It may return first 1024 bytes of large data, or fewer, depending on what's arrived. If large data hasn't arrived yet, delayed in network, the small data might be the only thing buffered yet. Delayed in the network. The small data might be the only thing buffered yet. So I think that's what was happening, because client side was using a single receive and was receiving the small message first. Doesn't that mean the large message was buffer delayed on send side? Like happened, server side did send large data, client side did receive. What TCP did under the hood, large data, small data were queued in the server's OS TCP send buffer in the correct order. But because large data was big, it got broken into many TCP segments, maybe 7 to 10 packets depending on MTU. These packets may take longer to transmit and arrive to the client. The small data likely got queued, sent, and ACK'd faster, possibly even in its own TCP segment, right after a partial large data. So when a client did it got whatever arrived first, and that may have been the small data, even though TCP is preserving order. The larger message was delayed in transmission order or being flushed from the kernel buffer. It wasn't reordered. It just hadn't fully arrived yet when the client first called received. Imagine you mailed a 10-page document and then a 1-page memo. The post office delivers the memo first because it's light fast and the mail truck had it near the top. The 10-page doc is still on the way. Nothing is out of order. It's just not fully delivered yet.
Is that it?
Okay, I'm still kind of like... honestly, I don't completely 100% understand. Like, I get the concept, but, like, I guess what I'm failing to understand is, like, in the analogy, like, do you have two trucks? So in the mail analogy sending side, do you have 2 trucks or just one? There's only one truck, but that one truck makes multiple trips. The first part of the big package is loaded onto the truck first, but before the truck finishes loading all the large data, the small package is ready and gets added to the back of the queue. So depending on how things are packetized, buffered, and networked, parts of the small one might fit into a new packet that gets sent faster. Okay. That's enough. That's enough. Like, I get the grand scheme. I don't need to understand all the fucking details of it. It's just kind of like... It's kind of a basic thing that you should understand, right? What's actually happening on the sending side. Your send is asking the OS to enqueue 10 kilobytes of data. The OS starts transmitting it in segments. 40-60 bytes per TCP packet. You immediately call send... So the OS starts transmitting it in segments. 40-60 bytes per TCP packet. You immediately call send, and the OS queues that too, just after the last byte of large data, on the sending side, right. But TCP stack doesn't wait for all 10 kilobytes to be physically sent before accepting the next call. It's like writing to a buffer. Think of it like one mail truck loading letters in a first in, first out bin. Sometimes a small envelope near the end of the bin can be delivered faster than the large stack that was added just before it. Not because it jumped a line, but because the first batch is still being handed out in chunks. I get it on a... Mostly. Moving on. Anyway. That was like a deviation. So, back to this. We have the... So this returns the hash token as a string. Now all we need to do is create the header. Let's see. So message header. Is a bytes object, and then it's good to be sent. So we'll say message header, network message header, which handles encoding internally. and then we send all. So then we have to, well then we have to concatenate, right? We have to concatenate the header string. Like we send the header, and then we send the data. Itself. Send the data, send the header, and then send the data. Oh gosh. Oh man. Oh. Client token. Okay, so we generate the client token. That returns a secure hash token as string. Return, let's say return type equals string. Return secure hash token as string. Okay. Then we have the encoded client token header. Using n.messageHeader, we pass in the client token. So it takes in the object, gets the size of the object. Wait, is it? Okay, yes, a string. Gotcha. Okay, so it takes in a string, it gets the size of the object, it converts that to a string, then it pads it, and then it encodes it, and then it returns the byte object size string. Okay, so that's good. Need to import n from network, so let's go ahead and do that real quick. Whoops. What? I thought it was Control Alt N to create a new. Oh, it's Control Alt Z. Yeah, Control Alt Z to create, and then Control Alt N. Okay, I got it. Okay, I see. Why is this bookmarked? Quite certain this is supposed to refer to the actual current card. Did we determine this is dead code? We don't execute the card. Did we determine this is dead code? Okay, so yeah, so we do have those bookmarks for a reason. So import n from network. Okay, so then we do con send all the encoded client token header. Then we do con send all encoded client token. First send from, this is a socket send, not network send. And we're going to fix that. We're not going to have that confusion because we're going to change the name of the send. And plus we don't use send, we use send all anymore. Okay, so alright, so this should be taken care of here. Okay, there we go. That's good. Now, okay, so this is going to verify the received. So basically this is just like we don't, this requires so much little subtle refactoring, honestly. Like it gives me anxiety for good reason. So I hate this little refactor type shit. It's just ugh. So many comments, like so many little tiny changes. Oh, you got to be so careful. If you do one little thing wrong, it's like fucking destroyed. And if you forget, you gotta like, oh, you just have to pay attention, like to such a high degree. The level of attention that it requires is it's crazy. Okay, so basically, I don't like bloat code, and I feel like all we're doing is we're just receiving like we normally receive. We don't actually need a get client token function. All this is the receive, like a normal network receive, where we do, like, it handles receiving the header. It decodes it. We get the header amount. We then receive the header amount. Then we convert it to its Python object. We decode it from bytes, and then we return that final object. So this is just a normal receive. The only difference is that we have this verify received. Okay? That's literally the only difference. And it's silly to have a whole nother function that all it does is do a network receive function call and then sends back a verify received. You know what I mean? That's silly. That's silly. So we're gonna change this. Like, we don't actually need we don't need this function. We're just going to put the verify received and the send all inside of the client. See, so let's see. Get client token. So we're not actually even going to use this function here. Okay. Okay, so we create the socket. That's the network socket. N.network socket. And then we connect to it whenever we call connect here. And then, so from that point on, we should be using, so con equals n.connect. So it literally just returns self.network socket compared to, so we just, so basically con is network socket. Oh, so we should just use pickle instead of JSON. Yeah, right. So pickle and JSON are just alternatives to one another. Where is it that we use the JSON? The fuck was it? I know we use it. Create token. Oh no, it's in the. I'm looking at the wrong file. Where's the shit? Hash token. There we go, JSON. So this should just be pickle instead. Okay. I was just thinking about if a client could connect to another. So spoofing. If the client said that they were like, well, but that would require hacking of the client, right? So like technically another client could hack this client to get their stored payload if it was saved to DB, and then they could spoof as that. They could spoof as that client, right? Okay, so anyway, we're done. That session, man, I tell you what, bro. Every little change that you make in a big project, dude, I mean, like, bro, once your project gets this big, every change that you make, like, you change 2 lines, dude, you gotta go and change, like, 20 other lines. It just takes... You're moving a big project, bro. You know? It's a large project. There's no way around it. But it just never ceases to amaze me how much creep there is when making like any change, you know, and as the project grows, the amount of creep grows, and it's just like, it's like a circle. It's not even like a line that gets longer. It's like a circle, and you have all these different like files as part of this circle, and like as the file grows a little, the whole project grows, and as you refactor, you have to refactor this entire circle. It's like man, it's wild, dude. It is just like, and you don't, like, if a circle gets a little bit, if a line gets longer, it's really easy to see, right? It's really just like to notice when a line gets longer. But when a circle gets, if you turn that line into a circle, or like a spiral rather, and then if you looked at it that way, the circle is only like, the line would go from this to this, but the circle is only going to go from like this to this. You can even see my hand move with the circle representation, because, or the spiral representation, because like it's just very subtle. You know what I mean? So it's a lot, and like we didn't really do that much. Well, we reviewed. We did improve. We really reviewed and improved this code, because like we said, this like, I hate bloat, and I'm very big on review and like getting it right the first time. I do kind of try to hustle, you know, like push myself to like just do it, you know, because I've learned review and prep and getting it right the first time is like very, very, very important. But I also understand that, honestly, I don't want to say always, but most of the time, it really doesn't matter how perfect you get it the first time, because you're probably gonna have to come back and modify it a little bit later. So like, don't, you know, it's like the graphics realism comparison. You know, get up to 90% realism, and then don't spend another 50% of that time required to go from 0 to 90 to get from 90 to 100% perfection. Leave it at 90% perfection, and use that 50% of time to move forward instead. And then when eventually you have to come back, you won't be like having wasted time perfecting something that might just get thrown away, or might just, you know, be modified a little, and it's just like, it just kind of nullifies that. So long story short, this wasn't necessary. This was like bloat. It's not a lot, but all the little it's not a lot adds up. It all adds up. As you can see, this project is like 20 something files or whatever. It's massive, and you know, it started off as just one little file, and that's just how it works with programming. So getting rid of bloat and repetitive code, or like, you see how we had this network socket, which is also basically interchangeable with the namespace con in client. That's like a big no-no for me. Like, that is confusing. You want one object. If it's the same object, you want one namespace referring to that object. And you want to catch that and get rid of the bloat, get rid of the weird code. You know, it's like a 90% thing. 90%, 90%. Don't spend too much time trying to get to 100% perfect. Get to 90% perfect, move forward. 90% perfect, move forward. You know what I mean? Be reasonable with your time. So the session, it was good. We verified the we really thoroughly reviewed this server code, so that's good. Forgot to put my double stamp of approval here on this encoded client header returns. Yeah. So anyway, we reviewed all this thoroughly. We fixed the code in network and figured out, we're just going to do a regular send with a normal header. So that like cleaned out some confusing weird spaghetti code bloat type shit to make it just we're using the same send function throughout, always. Very simple, very clean, love it. Lots of ugly comments and disabled code that we're gonna have to get rid of eventually, but we're not getting rid of no code until we do testing, because you'd be surprised, you're gonna want to look back at that disabled code and be like, wait a second, just trust me, we'll get rid of all that shit eventually, and it's gonna be nice and clean. So comments and disabled code is gonna stick around for a while. Unfortunately, it's very ugly to look at and it's kind of distracting, but that's the way it's got to be. It's like a job site. You need your tools and shit on your job site. You don't clean up the complete job site every single day. It's just not reasonable, right? Anyway, yeah, and then the client side has the basically final version of this receive for the client token, and we basically reviewed all that thoroughly. So we didn't get a lot, quote unquote, a lot done, but we did the right thing and we reviewed everything, and that is the most important thing. So yeah, anyway, I think I'm gonna go to the gym. I was gonna take the day off from the gym because I worked like 13 hours yesterday, but I didn't go to the gym because I worked. So I don't know, I think I do want to go to the gym. Anyway, we're probably gonna do that, and probably gonna eat a little snack before I go. And yeah, I'm probably not gonna code when I get back, honestly, because we did almost 2 hours. I may do another 30 minutes because I've been feeling real like spicy on finishing this shit, but we did 1.5 hours. We're still going, so this is kind of part of it. So it's basically 1 hour 45 minutes. But anyway, yeah, good session. We got how much do we have left? Let's look at things to do. We said we had like 6 hours, and that was before so I'll say like this is like probably gonna take me another 30 minutes for this one, and then some of these are like small, 15, so we're gonna say that's like 10 times 15 divided by 4, so that's like, well, we'll say 30 minutes just to be safe. So that's like 5 hours plus 30 minutes, so we're down to 5.5 hours roughly, maybe 5. I'll say about 5 hours more, so you're looking at about 4 more sessions roughly to knock this out. And so anyway, that's the deal. Have a good day. See you next time. Peace.